Hello students, today I would like to start the next unit in M1, sequences and series. What is a sequence? You know that the list of even numbers, the list of odd numbers, the list of Fibonacci numbers, these are all examples for sequences. Now let us see what is the definition of a sequence. Sequences and series. See the definition? A sequence is a mapping or function S from Z plus to odd. Understand? Sequence is a mapping S from Z plus to R. Z plus means set of all positive integers. R is a real number system. Okay. We denote the sequence by Sn or read as sequence Sn. Okay. That is sequence Sn is equal to S1, S2 and so on, Sn and so on. Okay. Here Sn is called nth term. Sn is called nth term of the sequence. Okay. For example, 1 by n is a sequence. That is 1, 1 by 2, 1 by 3, 1 by 4 and so on. Okay. This is an example for sequence. Next, constant sequence. Constant sequence. A sequence Sn defined by Sn equal to k for n. Sn equal to k for all n belongs to Z plus. Then this sequence is called a constant sequence. That is Sn here k, k, k and so on. That means all the terms of the sequences are k's only. Okay, this is constant sequence. Next, operations on sequences. Operations on sequences. Suppose Sn and Tn are two sequences. Then their sum Sn plus Tn. Sum of these two sequences is defined by sequence Sn plus Tn. Okay, and the product Sn into Tn, product of the sequences, is defined by Sn into Tn. Okay, and the quotient Sn by Tn is defined when Tn not equal to 0 for all n. This is called quotient of the sequences Sn and Tn. Okay. Next, boundedness of a sequence. Boundedness of a sequence. Definition. A sequence Sn is said to be bounded below. If there exists a number L. Such that L less than or equal to Sn for all n belongs to Z plus. Okay, then Sn is said to be bounded below. Here the number L is called lower bound. The number L is called lower bound of the sequence Sn. Okay, and if L is any lower bound of the sequence Sn, then any number less than L. That means suppose L1 less than L. Then L1 is also a lower bound of the sequence Sn. Understand? If a number is a lower bound, then any number less than that is also a lower bound. Okay? The greatest among all the lower bounds of a sequence is called greatest lower bound. The greatest among all lower bounds of the sequence Sn is called greatest lower bound, or simply GLB, means greatest lower bound, or also called infimum of the sequence Sn. Okay. Next definition. A sequence Sn is said to be bounded above. A sequence Sn is said to be bounded above if there exists a number u belongs to R. There exists a real number u such that Sn less than or equal to u for all n belongs to Z plus. Sn less than or equal to u for all n belongs to Z plus. Then this u is called upper bound of the sequence, and in this case Sn is said to be bounded above. U is called upper bound of the sequence Sn. Okay. And remember one thing here, if u is an upper bound of the sequence Sn, then any number greater than u is also an upper bound. Suppose u is less than u1, then un is also an upper bound. Okay. The least among all the upper bounds of a sequence is called least upper bound, or simply LUB. This is the least among all the upper bounds of the sequence. Okay, is called supremum. Least upper bound or supremum. Next definition: bounded sequence. Definition: the sequence Sn is said to be bounded. Is said to be bounded if it is both bounded below and bounded above. Bounded above. If it is both bounded below and bounded above, then the sequence is bounded. Okay. Or if there exist some real numbers k1, k2, such that k1 less than or equal to Sn less than or equal to k2 for all n belongs to Z plus, then we say that Sn is bounded sequence. Okay. Say an example for bounded sequence. Sn equal to 1 plus minus 1 whole power n. That means the nth term is 1 plus minus 1 whole power n. Then what are the terms of the sequence? The first term is 0. The next term is 2. Next 0, 2, 0, and so on. Okay. That means the range of this sequence is 0, 2, which is bounded. Okay. And hence this sequence is bounded. Next definition: monotonic sequence. Monotonic sequence. The sequence Sn is said to be monotonically increasing. Monotonically increasing if Sn less than or equal to Sn plus 1 for all n belongs to Z plus. Okay. Next, Sn is said to be monotonically decreasing monotonically decreasing. If Sn greater than or equal to Sn plus 1 for all n belongs to Z plus. Sn greater than or equal to Sn plus 1, then you say that Sn is monotonically decreasing. Next, monotonic. Sn is said to be monotonic if it is either monotonically increasing or monotonically decreasing. If Sn is either increasing, that means monotonically increasing, or decreasing, then we say that Sn is monotonic. Okay. Next, convergent sequence. Convergent sequence. A sequence Sn is said to be convergent. Is said to be convergent if for each epsilon greater than 0, for each epsilon greater than 0, there exists a positive integer m. There exists a positive integer m such that modulus of Sn minus L less than epsilon for all n greater than or equal to m. Okay. In this case, we say that Sn is convergent and Sn converges to L. The sequence Sn converges to L. And we write limit n tends to infinity. Limit n tends to infinity Sn is equal to L. That means that sequence Sn converges to L. And here L is called limit of the sequence. And this L is called limit of the sequence. Okay. Next, divergent sequence. Divergent sequence. A sequence Sn is said to be divergent. Sn is said to be divergent if it is not convergent. If it is not convergent. Okay. And divergent sequences are classified as diverges to plus infinity, diverges to minus infinity, and oscillates finitely. Oscillates finitely. Next, oscillates infinitely. These are types of divergent sequences. Now, what is meant by oscillates finitely and oscillates infinitely? Oscillates finitely. A sequence Sn is said to be oscillates finitely. Oscillates finitely if Sn is bounded but not convergent. If Sn is bounded but not convergent. Okay. For example, minus 1 whole power n. This is the sequence. That means the terms are minus 1, 1, minus 1, 1 and so on. Okay. Now, the range of this sequence is minus 1, 1 and hence it is bounded but not convergent. Okay. And hence this is oscillates finitely. Next, oscillates infinitely. Oscillates infinitely. A sequence Sn is said to be oscillates infinitely if Sn is neither bounded nor diverges to plus or minus infinity. That means it is not bounded and it is not divergent to plus infinity and minus infinity. Okay. For example, minus n into minus 1 whole power n. This is a sequence n into minus 1 whole power n. Here Sn is n into minus 1 whole power n. What is the first term? Minus 1. Next 2. What is the next term? Minus 3. Next term is 4 and so on. Okay. This is not convergent and this is not divergent to plus infinity or not divergent to minus infinity, and hence it is oscillates infinitely. Okay. Next, infinite series. Infinite series. An expression of the form u1 plus u2 plus u3 plus u4 plus and so on. This is called an infinite series. Okay, where un is a sequence of real numbers. Okay, u1 plus u2 plus u3 plus and so on. This is an infinite series, and it is denoted by sigma un. N is 1 to infinity. Infinite series is denoted by sigma un. N is 1 to infinity. If the terms of this series is finite, then the series is called finite series. Otherwise, it is infinite series. Now, when the series is convergent or when the series is divergent. Convergence of a series. Convergence of a series. Let sigma un, n is 1 to infinity. That means u1 plus u2 plus u3 plus and so on be an infinite series. Okay. Let Sn equal to u1 plus u2 plus u3 plus and so on plus un. That means sum of first n terms in the series. Okay. This is called nth partial sum. Nth partial sum. Okay. Now we have a sequence Sn. This is sequence of partial sums. If this sequence converges to a number s, that means sequence of partial sums converges to a number s, then you say that the series converges to s. Okay. That means if the sequence of partial sums are convergent, then the series is convergent. Okay. And in this case, we write sigma n is 1 to infinity un is equal to s, since the series is convergent to s. Okay. And here s is called sum of the series. Sum of the series. Okay. If the sequence of partial sums is divergent, then you say that the series is divergent. That means sequence of partial sums, that is Sn, is divergent, then the series is divergent. Okay. If the sequence of partial sums Sn oscillates finitely, then the series oscillates finitely. Okay. If the sequence of partial sums oscillates infinitely, then the series oscillates infinitely. Okay. Next problem. The geometric series a plus ER plus ER square plus and so on, where A greater than 0 is convergent if minus 1 less than or less than 1. Next, diverges to plus infinity if r greater than or equal to 1. Oscillates finitely if r equal to minus 1. Next, oscillates infinitely if r less than minus 1. Okay, this is the geometric series A plus AR plus AR square plus and so on, where the common ratio is r. Okay, see the solution. First one, suppose minus 1 less than or less than 1, that is modulus of r less than 1. Okay. Let Sn, the nth partial sum, is A plus AR plus AR square plus and so on plus AR power n minus 1. This is sum of first n terms in geometric series. This is equal to A into 1 minus r power n by 1 minus r. Okay. Now find the limit of this sequence. Limit n tends to infinity Sn is equal to limit n tends to infinity A into 1 minus r power n by 1 minus r. Okay. This can be written as A by 1 minus r minus limit n tends to infinity AR power n by 1 minus r. Okay. But what is the limit of r power n as n tends to infinity? Says, since mod r less than 1, limit r power n as n tends to infinity is 0. R power n tends to 0 for mod r less than 1. That's why this becomes A by 1 minus r minus this becomes 0. Okay, that is equal to A by 1 minus r. Okay, that means limit Sn is A by 1 minus r. That means this limit exists. Okay, hence the partial sum sequence Sn converges, and hence the series convergent. Hence the given series is convergent. Okay, that means the geometric series is convergent for minus 1 less than or less than 1. Okay. Now case 2. Suppose r greater than 1. Then you know that limit r power n as n tends to infinity is plus infinity only. Okay. So now what is Sn? Sn is A into r power n minus 1 by r minus 1, since here r greater than 1. Okay. Now what is limit Sn? Limit n tends to infinity Sn is equal to limit n tends to infinity A into r power n minus 1 by r minus 1. This is equal to plus infinity. Since limit r power n is plus infinity, this becomes plus infinity. Okay. When r greater than 1, the sequence diverges to plus infinity, and hence the series diverges to plus infinity. Okay. Suppose r equal to 1. Suppose r equal to 1. Then Sn. Sn means sum of first n terms in the series. That is A plus ER plus ER square plus and so on. But since r is 1, all the terms are A's only. A plus and so on plus A. This is n times. This is equal to Na. Sn equal to Na. Therefore, limit n tends to infinity Sn is equal to infinity. Since here A greater than 0, limit n tends to infinity Sn is infinity. If r greater than 1 and if r equal to 1, limit Sn is plus infinity only. That means the sequence Sn diverges to plus infinity. Hence, the given series, that means the geometric series diverges to plus infinity. Okay. Next one. If r equal to minus 1, then Sn is equal to a minus a plus a minus a and so on. N times this is. Hence Sn becomes 0 or a. Sn is 0 or suppose S1 is a. S2 a minus a 0. S3 a minus a plus a, that is a. That means Sn is nth partial sum Sn is 0 or a, and hence Sn is bounded. Sn is bounded but not convergent. And hence Sn oscillates finitely. Hence the series, hence the given series oscillates finitely in case of r equal to minus 1. Next, last case. Suppose r less than minus 1. R less than minus 1. Then you can write r equal to some minus t with t greater than 1. Okay. Now the nth partial sum Sn is equal to a into 1 minus r power n by 1 minus r. Okay. That is equal to a into, what is r here? Minus t. That means a into 1 minus t whole power n by 1 plus t. 1 minus t, 1 plus t. Therefore, Sn equal to, suppose n is odd. If n is odd, then minus 1 whole power odd is minus t. Okay. Then a into 1 plus t power n by 1 plus t if n is odd. Okay. If n is even, minus t whole power even number is t power even. Okay. That means this becomes a into 1 minus t power n by 1 plus t if n is even. Okay. Therefore, limit Sn as n tends to infinity if n is odd is plus infinity if n is odd, and limit Sn as n tends to infinity if n is even, then t power n is tends to infinity as n tends to infinity, then 1 minus infinity is minus infinity. Okay. That's why this becomes minus infinity if n is even. Okay. This means this sequence neither diverging to plus infinity nor diverging to minus infinity, and hence this sequence oscillates infinitely. Hence the given series oscillates infinitely. Okay. Next, necessary condition for convergence of a series. Necessary condition for convergence of a series. If sigma un, n is 1 to infinity, converges, sigma un converges, then limit un n tends to infinity is 0. That means the series converges, then limit un is 0. Okay. The converse of this is not true. This is the necessary condition for convergence. The converse is not true. That means if limit un is equal to 0, then sigma un, the series, need not be convergent. Need not be convergent. Okay. And note, now, if limit n tends to infinity, un not equal to 0, then the series sigma un, n is 1 to infinity, is divergent. This is the contrapositive of this statement. Okay? If limit un not equal to 0, then the series is divergent. Okay? Okay, students. Thank you so much for watching. See you in the next video.